value, right? And I said that I would just use this full width because you have an I-beam. I would use that for my B, and then my D would be the standard D down to the thing there. Anyways, so you'll get an exercise of playing with this. The other way to do it is strain compatibility, right? As a academic, I would do it this way, right? Because this is the way I would want to do it, right? Because I have extra time and I can work on stuff like that, right? But then you as real engineers, you're not going to do that, right? You're not going to do that. Or you might, and then you'll get fired because you took extra time to do something that should have been really quick. Right? Here's some coffee. Okay, so that's what we briefly, and so I'm just going to skip, because I used to have you do it, right? I'm not good anymore, but I still want to talk about it a little bit, okay? So that's what I'm going to do. That's what we're in the middle of discussing, like what would actually happen here. As an academic, I still need to show you, right? So this is the same thing happens. We still assume the 0.003, and then we have this epsilon down here. We're straining the steel, okay? And then we have, again, 0.85 F prime C. This is beta 1 times X, or what we call A, right? And then this is FPS down here, okay? And so we can actually do this, right? So there's the steel starts out and it's strained to begin with. Right, so this is our FPS versus epsilon sub PS. Right. It starts out, like I said, being strained already. We'll call that epsilon PE. Right, that's elastic pre-stressing. Right. Then there's another strain that goes right here. And we'll call that is decompression, right? And then there's last one right here. That strain out there would be epsilon PU. So they're all additive as they go along. Epsilon PE, and this would be epsilon PD. So there's three different strains floating around. And this is where it gets really confusing. This one makes sense to me. This one's really easy. The epsilon sub PE, this is how much you strained it to begin with. You pulled it back, you cast the concrete, you release it, it squishes it, right? And so it will have a pre-stressing strain in it, which is called, that's where you're getting your FPE from, is from this epsilon sub PE. This decompression strain gets a little bit weird, and it's basically getting back to the decompressed state. Now, that's all I'm going to say is getting back to and then this epsilon sub PU that you see here is this strain that we have right here. It's the additional strain that gets added to the beam when we start bending it. Okay, that's what the epsilon sub PU is, right? So you have these three strains going around. So you actually have to calculate this. So the equations for doing this, for calculating FPS, you would calculate what epsilon sub PE is. There's an equation for that. There's an equation for this. And then this epsilon sub PU is going to be a function of the neutral axis depth, right? Because depending on, right, if X gets bigger, right, if this goes down, then I get less strain. If X gets smaller, I get more strain, right? And so it's a function of, just like it was in regular reinforced concrete. It's a function of that. So you have these three strains floating around, and then you have to apply equilibrium, right? And then you have to have, that's about all I'm going to say at this point. That's just going to confuse even more if I keep talking. Uh-oh. It's showing in there. It's not showing here. Oh, weird. That's so weird. Okay, I was like, what? Why are you guys laughing? You can't see anything. I updated my operating system last night. I should have done it. Turns out, this is a problem that they have. Well, that's not what I meant to do, but T equals C, that works, right? C and T. Oh, it's
mute. It's going backwards. Your operating system is screwed up.
It's my fucking operating system. That's what I get for updating. It just came out yesterday, too. My operating system, and I was like, hell yeah, I'm upgrading. Turns out, what I do, so this is what happens, is we get it. So they come out with a new operating system. And then Ernie sends out an email saying, don't install the new operating system. But that takes a couple days before they do it. So I install it before they say don't do it. See? The loophole, Sean? The loophole I got?
You want to tell him that he needs to hand delivery to a note like 3 days before he gets
Yeah, they need to pay closer attention.
I think it should go fault.
I guess I'm going to type it. I guess I'm going to write it. So good luck reading my shit here. Okay?
Type backwards.
No, I guess I could type backwards.
To see how that goes.
Right. We set C equal to T, right? C and T are functions of neutral axis depth, right? Which is A, right? Both of them, the C and the T, are functions of the neutral axis depth, right? And because there's functions of the neutral axis, you have to solve them both at the same time, right? Because they both are affected by it, right? Yeah, and then, I mean, that's it. That's where, so you set C equal to T, solve for neutral axis, right? Some moments to get MN. Those are standard stuff. This is exactly what you did for over-reinforced beams. If you ever did, remember over-reinforced beams? T was a function of the neutral axis depth on one side because it hadn't yielded yet, right? It was somewhere, right? For over-reinforced beams, your steel stress was somewhere in here. So it's the same idea. We don't know where it's at in here, and it's dependent upon where the neutral axis depth is over here because of that. And so it's the exact same idea. It's just in over-reinforced beams, it was just the relationship between FPS and epsilon sub P was just E, right? Epsilon sub P times E gave you what your FPS is, right, in that region. Okay, I mean, it's the same idea. And so then when you solved, you remember this. In Structures 2, you had to do it in one of the homework assignments. You had to set C equal to T for the over-reinforced. In your lab, you had to do it. And then you probably use goal-seek. You may have used goal-seek in Excel to find the neutral axis that made that work, right? And so, or another way you could do is you could plot C and T, and then you see where they cross each other, and then right where they cross each other, that's where that'll give you the neutral axis. Anyways, there's different ways to do it. Same idea. It's just now instead of being just FPS is equal to E times epsilon to PS. That's what you did in Structures 2. You have to use this, right? You have to have an equation that relates the two together. So down in here, it will be elastic. It'll just be epsilon sub PS times E. That's how the relationship between the two. Or it's this whole thing, right? It's this whole equation. This is called the Minigato-Pinto. So this is what I'm saving. You used to have to do this in a homework. You had to program in Minigato-Pinto, and then you had to put it in there, and then you had to and then you had your T would be this, which would be a function of neutral axis depth, but it had it would have three strains that are floating around that are in there as well, and then you would set C equal to T, and then it was a big deal. It was super fun. For me, it was super fun, but I'm not going to make you do it, okay? You're welcome.
Thanks.
Yeah. Maybe we should do like a drawing. If somebody's not here, the penalty is you have to do that. If you want to pass the class, you have to program strain compatibility. Okay. And so the rest of this stuff, I mean, that's all I want you to understand is right? It's a function of the neutral axis depth. The T is a function of neutral axis depth. It's just like over-reinforced. Just like over-reinforced. But strain to FPS Oh, I don't like type. I don't like writing. You don't like me writing either. Is this. Okay. So I think that hopefully you could just look at this and be like, oh, I could do this if I had to. Luke, could you do this if you had to?
Maybe.
Okay, there you go. That's all I want. That's all I want. Thomas, could you do this if you had to?
I wouldn't want to.
Yeah, okay, but you can do it. Noah, you got this? If I figure it out, yeah. It's just get that general concept, and it's called strain compatibility. I don't know why. I mean, no, it's because you're assuming, right, this strain is compatible, and you're going to find that neutral axis such that it happens. I think you can also plot. Anyways, just that's what it is. It's just you dive in deeper and you assume that the strains in the concrete are the same as the steel, and so this is like Stanton. This is all in Stanton's notes talking about. Well, this is the epsilon sub PE, the decompression strain, and then the strain after that. This is what I was saying. This is what we've strained it to before. This is the decompression strain, getting you back down to 0. That's the epsilon sub PD, and then from there it becomes that's the epsilon sub PU value, right? And so we're not going to do that. But here's all the equations for what all of those things are and whatnot. Okay, so putting it all together, regardless of if you're using no matter what method it is that you're using, I'm just going to lay it all out in one spot, right? Just beating this horse to death, right? You start out, goes like this, right? Right. This is 0.003. That makes a difference because we still have phi factors floating around. We still need to do these calcs, right? That one's epsilon sub PU, right? That goes to stresses, right? We're going to go straight to the Whitney stress block. Right. Again, this is 0.85 F prime C. Right. This is beta 1 times x. This is A is equal to beta 1 times x. And this down here is FPS, right? And we're going to, in your homework, you're going to do it once with this equal to Fy or ACI equation. Right. Instead of calculating it as a function of the neutral axis depth, the ACI equation is just going to give you a value for FPS. It should be close to Fy, right? It should be close to Fy. Given that, right, then we could calculate what this is, my C, right, and then my tension down here. Right. My C is going to be 0.85 F prime C times the area, right? And this area is going to have A in it. Right? The neutral axis in it. And this T down here is just going to be FPS times the area of the pre-stressing. Right? And the reason I say area is if it's a rectangle, it's B times D. But if it's an I-beam, it's the area over which it acts. If it's a triangle, it's the area over which it acts, right? It's the area over which it acts. And your homework is a T-beam, right? Or it's an I-beam, or it's something. I don't remember what it is, but your homework's going to be one of those. It doesn't matter. It has a web and a flange, right? And so then to do that, remember, I always like to do it like this. I like to break it up like this. I wonder if what it does. Oh, look at that. Right. Okay. I like to do it this way. Because it would be too easy if I just left. If I left it up in the web, right? That's pretty easy. That area is pretty easy, right? That's just beta 1. But that's no fun, right? So I'm gonna put it down. I'm gonna make it go down into here, right? And so I like to do it. This is how I like to do it. I like to go like this. I like to look at that area, right? And then these areas. Right.
Why?
Because this is just A. Or you could just say A minus C. Either way, you could do whatever. Or you could do A minus TF. Which one do you like to do? You don't like this?
I like to do the full area on top.
Yeah, and then the other one. So then when you calculate the area, it'll be TF minus. It'll be A minus TF would be the area that it gets multiplied by. Right. I'm a doctor though, so I have to listen to me. I like to do it that way, or you could do it. It doesn't matter, right? But that's what I'm saying. The area, and this is what I'm saying. It has the area. It has A in it, right? It has A in it because that's the unknown, right? That's the only thing I don't know in this case, right? When you're doing the other method, you don't. This T down here is a function of A as well, but in this case, it's not a function. When you use one of these two methods right here, it's not a function of A. It is just a number, right? And so the only unknown is that neutral axis depth. Do it how you see fit. I like to do it that way, but that just gets you thinking about it like that, right? So then down here, like, what do? Well, you set C equal to T, right? You solve for you solve for A, right? Then you sum moments, and that gives you Mn, right? And then one thing you'll have, the reason you need to know that neutral axis depth is because you need to know this, right? What is the distance in between them? And that's going to be a function of the neutral axis depth, right? This distance here, that distance there is D, right? And so it'll be, D minus something, right? Okay. Or if you've done it like this, right? And so I'm getting ahead of myself, but you'll see, if you do it like this and just have one C, then you have to find the centroid of this because that C is going to act through the centroid of this. Or, right, if I did it this way, I like my way, bastards, right? It's easiest to put it in as two forces, right? You have this C for the flange, C flange, and then you'll have a C web. Right? That's how I like to do it. I like to break them up like that. Huh?
Either way you break up the areas when you do that?
Either way you break up the areas, right? Or you can find the centroid of the little guy. Well, that's stupid. Don't do that, right? Do it as right? Do it as this, right? I would do it as this, right? And so you would have, and then where these are located is based on how you broke it up. Look at this one. See, Thomas, right? And Kira, right? If I do it this way, it's right in the middle. This one acts at TF over 2, and then this one acts at A over 2.
Then your CW is it's like in the flange.
Or you can
Yeah,
just
because
do-
either way, it's still two
Whatever.
rectangles.
It's
just
two
however
rectangles. It's two rectangles. It's not hard.
Rectangle works better for your brain.
That's right.
Not that one.
Anybody on my team? Anybody on my team on this? Thanks, Noah. Yeah, right. Noah gets an A. I'm gonna grade it solely off of how you break this thing up like this. Let's see what you do.
I feel like that's the easier way to do it if you're programming it. But the other way is nicer if you're just handcalculating it.
Yeah, if you're simple. If you're simple, you're probably taught that way, right? I mean,
I learned from Kirsten.
Kirsten did.
You can have an argument with her.
Yeah.
I'm gonna tell her you called her Kirsten. First of all, I'm gonna tell her that, Thomas. Or if you really want to piss her off, call her Kristen. Do it. And then sign your emails to her. Hey, Kristen. She freaking hates it. But I just think it's like, they're so... Technically, I think her parents spelled her name wrong. Because, right? That's how you spell Kirsten, is K-I-R.
I knew a girl named Kirsten and it was spelled the same. That's why
That's
I was
right.
asking about.
Yeah. Siri says, if you've ever talked to Siri, Siri says it's Kirsten.
That
Yeah.
was Kirsten until this year.
Oh, really?
Yeah.
Yeah.
I called her that.
Yeah,
She's
she
like,
does not like that.
Yeah. I do it on purpose. I said always on purpose. Because I know it pisses her off. Do it. You should all start doing it.
Did like your fourth order beam way of looking at it better?
It is
That
better.
worked.
It is, right? It works out beautifully. Okay? Does that make sense? And so here, right? again, break it into two. It's easier because then now when you get down to this, when you're summing the moments, right? You pick one of these things and you sum the moments about one of those things, or you could sum them about the middle, or you could sum them about the end. You could sum them about wherever point you want. But then that's where you get an MN from, is from summing those, okay? And so that's what I'm asking you to do, is just to do that. So that's all in one place, right? So hopefully, like I said, I'll assign it today, and we'll have it due next Friday. I'll give you a little more time. I'll have it due next Friday. And go from there, right? Because I know that some of you will be working on this homework until late this evening. Okay. That's your statement, Luke?
Maybe. I'm close. Might get it done.
Okay. All right, so unbonded post-tensioning, right? So this is, by the way, all this stuff has been for bonded post-tensioning at this point, right? Unbonded post-tensioning, so this would be post-tension, right? Unbonded, where it's not stuck to the concrete. When it's not stuck to the concrete, there's no such thing as strain compatibility because they're not compatible, because they're not attached to each other, right? This assumption up here, when even though we're not doing strain compatibility, this equation is based off of strain compatibility, is how they developed it. But the strain in our steel is the same as the strain in our concrete. That's a fundamental assumption in this. When you have post-tensioning, that's not the case. They're not attached to each other, right? And so if you strain the steel, it's, instead of having it localized in one location, it's spread out along the entire length because it's not bonded to it, right? And so basically there's only really one way to do it in unbonded post-tensioning, and it's just to use this equation that they give you here. Right? They just basically give you an empirical equation, and you use that. Let's see if I say anything else. Oh yeah, so then we'll write that. Oh, that's not. Oh, I can't type. Fuck. This is a paragraph. God damn it. I just want to write that down in one place. I want to focus on writing. Ooh, look at that. Pat, ability.
You don't have to spell check.
I know. So does not apply to unbonded tendons. That's not so hard. Must use empirical. We're going to just use empirical anyway, so in the past when I used to have people do strain compatibility, it was a little more involved. Man. Should have waited for Ernie to tell me not to do this. Certain things aren't working. Okay, so you just have to use one of those empirical equations. Okay, so there is still strength reduction factors floating around. We still need a phi factor. Okay, phi factors that we have to use. Right here. Right, this is section 21.2.1, tells you what phi factors to use for the different members, right? And it turns out it's the same thing, right? It's the 0.65 to 0.9, right? Depending on the strain in the steel, okay? And it's the exact same relationship, right? Same, right? I got it written right here. Same as for reinforced concrete. The one thing, though, right, is what do we use for that strain? Right? What do we use for that strain? There's multiple strains floating around, right? It's already strained, right? It's already stretched out to a certain point before it even starts. We wouldn't use that value, right? That value doesn't tell us anything, right? and we're moving to the right of that. What we really care about is what the last one is, what this epsilon sub pu is. We care about this epsilon sub pu, even though there's other things there, right? It's already been stretched and it's already been there. The reason we care about this one is this is the one that you would see if there's a failure, right? You don't see the pre-tension strain, like it's already squished. But when it's gonna break, like you would see this much strain. And that's what would be evident. That's the curvature. That's what you would see. But why do I care if I can see it? It's a warning, right? If you look up at a beam and you see that shit hanging down, right, and it's sagging, you're like, I'm getting the fuck out of here, right? That's the whole point, right? Is like you'll see this excessive strain. You won't see these strains, right? These strains you don't see because that's the pre-stressing, right? You don't see them. And so the only one you care about is the last one. So it's a little weird that that's the case, but that's what it is, right? We use the epsilon, what do I say here? We use this one, right? And you calculate it the same way you do for regular reinforced concrete, right? And it comes from this, right? Oops. Here. Epsilon sub pu. This is what you see before failure. I just use a mix of capital and lowercase. I don't know how it happened. I don't know how. I still have one cursive letter survived. If I write the word of, I throw it in lowercase f. Right? Look at it. I start out, right? Everything's good, right? And that's good. Oh, capital B. Right? Oh, capital E. Oh, failure, capital A. Capital R. Capital E on the end, right? That E is capital. Those other ones are small. I don't know. I don't know what happens. It's like a small child's writing. That's why this is typing saved my life, right? Because I used to have to do this on the board in front of everybody, just like that. Everybody's like, what the fuck is this guy doing, right? You might think that anyway, but it's even worse when I'm writing, if I'm going around writing like this. Now you understand why I type everything, right? Now you get to see it, right?
Well, you could still type it like that.
I could, just all the ups and lower cases. Tim White used to have terrible handwriting. And then when he went to Morrison Valley, how he fixed it, because as he just said, everything's caps.
That's what I do.
And if you go everything caps, then it forces you to change the way you write, and then go, I can't do it. I tried doing it right here, where I wrote strain, and then I got tired of it. I was like, fuck it. I was like, I'm gonna write everything in caps so they could read it, and I was like, fuck it. And then I just, compatibility's all caps. Oh, fuck, two eyes. Honestly, I remember when I got to those. Damn it. When I got to the eyes, I was like, I'm not going to do this.
You got to be.
Yeah. When I got to B, I literally remember writing the I and go, well, there goes that. I said, there we go.
He does cross the line.
I can't do it.
He could be trying to get out of P though.
Yeah.
Actually, yeah, go back up.
You want to see my the I's, right? The B's, everything's good.
What about equation?
Yeah. Okay, but he should something about that.
He's got rubber
E, yeah. See?
Why is the key
Dude, I think let me just look. I think I wrote an of above.
It's just massive.
Oh, it's down a little.
Did I write an of?
Yeah. Oh, no.
No, that's
I do it. It's in one cursive survived. Did you guys learn cursive in high school?
High school.
I mean, sorry. Well, Billings. I don't know what they're doing in Billings.
You were in Missoula for elementary. Yeah.
Oh, so they taught you cursive. Did you guys learn cursive?
First grade.
Yeah.
That's stupid.
They canceled it like halfway through me.
Yeah, I literally, I think the only reason to learn cursive nowadays is so you can read your grandparents' writing, right? And what's that?
Signatures.
Signatures too. You know,
You only have to know one signature. That's all I know.
My kids are writing their signatures because they don't know cursive. And literally, they'll get a card from their grandparents, and my wife and I have to read it because they can't read the cursive that's been written. Isn't that interesting? They shouldn't be teaching typing. That's what they get. I know, but my kids have tried getting in. They don't offer it at Gallatin High. And so they just leave it to you to learn typing. Do you know how to type?
Yeah.
Who all in here knows how to type correctly? Correctly. Without looking at the keys. Did you learn that in high school? Matthew, you're out of that?
I middle school this summer.
Who doesn't know how to do it? Really? You know who else doesn't know how to do it? And I think it's fucking hilarious. It's Tim White. He has to, you watch him, he's a hunt and pecker, right? He looks right at it. He's like, where is that? And there's the two fingers go, he's an idiot. He looks like an idiot. And that's what I think this.
Getting used to knowing where
The QWERTY keyboard.
Random letters.
Yeah.
Yeah.
Yeah, and you got to look at my football coach taught me typing in freshman year. So that's what his job was at the school, was teaching typing. I currently have an ongoing with my kids right now. It started out, I offered them $200 to be able to type 60 words a minute without looking at the keys. And both of them have yet to do it. So this year I upped it because I was like, my son's 18, he's graduated. It's like, I cannot have you, I make fun of people, I cannot have one of my own spawn come out and not know how to type. It's up to $300 at this point. $300 if they learn how to type. And they have typing tests. Now, especially with online tools, like you could just go through and progress as you're going along, right? Maybe I'll offer Tim $300 if he could type 60 words a minute without looking at his keys. It's honestly a skill that I picked up in high school that was just like invaluable, right? Being a Curie, you're missing out. You're missing out, right? You could type.
The problem now, though, is like, especially like with anybody that plays video games on keyboard,
Yeah.
their hand is starting to dock more towards the WASD side instead of to the south.
Oh.
One of the three I was talking about.
Kira's throwing shade.
I'm fine with that.
Yeah. Fuck her up, John. Get her.
Fight.
Fight.
Bring the gloves in on Friday.
Yeah. And so, okay, back to this. Right. This is the key to this is you've solved for that neutral axis. This is just review, right? That you've solved for that neutral axis. And so that distance x is equal to a over beta 1. Okay? And so you could get what that x is, and then this up here is 0.003. Right, and so given that, based on similar triangles, and you just solve for, like, again, this is fixed at 0.003. You just solve for what a needs to be. You then a over beta 1 tells you that distance x, and now we have that x, and based off of similar triangles, you can get what epsilon to pu is, and then based off of what your epsilon to pu is, you then come up and you use. Use this 0.65 or 0.9, and it varies, right? It's right here, right? It varies. It starts out, depending on if you have spirals or either spirals or ties, which will have ties, and then it goes like that is what it's going to end up being, right? And so it's based off of what the ET and epsilon sub t is this epsilon sub pu right here, right? And so it increases based off that, and that has to do with warning, right? Something that has 0.005 for strain has that much curvature, you would see that, and so you get rewarded, and you get to use 90% of what the capacity is that you calculated. If you have a strain that's less than that, which is, it tells you right here, there is no yield strain in steel, and pre-stressing. So there's a little section in the code that says make that 0.002. For pre-stressing, use a 0.002. So if you go less than 0.002, then you use 0.65, right? And then in between, it ramps up, right? And then you're like, oh, in regular reinforced concrete, you couldn't do this, right? You couldn't make if you remember back there, you can't have a beam that's over-reinforced. Do you remember this? Right? We teach you all this in structures too. You're like, oh, look at that. But then, oh, by the way, you have to be over here. There's a section in the code that says you can't even be over here, dummy. You have to stay. You have to make it this other thing. But there is an exception. There's something else. a reinforcement strain limit in non-pre-stressing. And so basically, there is no limit. If you read the thing that says you can't do that, back in the section, it says you have to have at least 0.005, it says if there's no axial load on it. This has axial load on it. Where's the axial load coming from? The pre-stressing, right? The pre-stressing is there that's causing that, and so you're allowed to do it when you have that axial load. And so that's just a side note. So if you end up with a phi equal to 0.65, that's okay, right? Regular reinforced concrete can't do it. Your strain has to be at least 0.005, but pre-stressed concrete you can. You are over here, right? Columns also are a case where you're over on this side where you're allowed to do it. I think that's what this footnote is discussing right there. Okay, all right. Okay, that's cool. We'll talk about this next time. There's a minimum amount of pre-stressing or a minimum amount of reinforcement in general that has to be included in pre-stressed beams because you can't have cracking failure. So in the meantime, I'm going to look up